Okay, in the interest of time, I'll make the introductions fast. I will not read what you've already seen. You've already seen paragraphs about all the members of my team. The reason it takes a team to do this is because one of the key things we believe, and that we've discovered, I guess, now that we've been through some experience with smart labs, is it takes a comprehensive redesign and questioning everything in the building's mechanical functions from the foundation to the roof. And only by doing a complete, comprehensive, holistic analysis of it is it possible to achieve the kinds of savings we've been getting. So that's why we have a team here. And besides that, you wouldn't want to listen to any one of us just go through all of this. So it breaks it up a little bit. I'll introduce the members of this group in the order that they'll speak. Matt Gudorf, I think one of the things it didn't say in Matt's write-up was something he doesn't like to brag about, but I don't mind, and that is Matt is the 2012 Energy Engineer of the Year as presented by the Southern California chapter of the Association of Energy Engineers. I can tell you there are a lot of energy engineers in Southern California, so that's a pretty significant recognition that he received from his peers. I've already talked quite a bit about Mark Gomez. I've told you that he is one of the key people, if not the key person, responsible for the remarkable improvement in campus safety that we've experienced, particularly when he was in charge of environmental health and safety. He's now in a broader administrative role, but his roots are in environmental safety, and he's done a lot to put Irvine in the position that I showed you a few minutes ago. David Kong is the youngest member of our group in a way, or at least he's the newest. You're also the youngest. And he replaced someone who retired, Lisa Mahar, who I think may be someone whom some of you know because she had a long-standing reputation in environmental health and safety. David, one thing about David that's interesting is he's done some really significant volunteer work in humanitarian areas, and in particular, he served in the United States Peace Corps. And it shows the kind of compassion he has for people, and that's actually the exact kind of person we want on the team who cares about safety. And so that's his very significant role. And then Fred Bachmiller, who will be batting cleanup. Fred has been part of this energy team even before this team you see here formed. He was there 2 decades ago when we first started at UC Irvine with that process I described where we decided to start beating California's energy code, and then we did a lot of things that Fred thought up and helped to lead in the central campus infrastructure, such as our combined cycle cogeneration, our massive thermal storage system, all kinds of things in the infrastructure which have actually been just as important as what we've done in the buildings themselves. So Fred is a chief engineer on campus. And I won't say any more than that because you can read it here. So, Matt?
Thanks, Wendell. Good morning. If everybody can hear me, I'm probably not going to stand up here, and I'll probably do kind of the walk and talk thing. It's more comfortable. I'm really excited to kind of come in this morning and really address the Smart Labs program that UC Irvine has put together. And again, it is a program. But I guess the first thing I want to do is I want to try to ask you today, while we're presenting, while the team's presenting, draw from what you heard this morning, from what Wendell said as far as setting a policy on campus, for what Phil said on how you need a roadmap, you need a dashboard, you need to be able to see these things, you need to make these items actionable, and then Alan, what they're putting into practice. You're going to see some of that. You're going to see a different take on it. This is a program that works for us, for UC Irvine. But you want to take the different pieces and say, okay, if we like this piece, how can we incorporate it, or what are they doing in their area, and make that program work for you. So that's what we're really looking for, and that's how we really want to go forward. So smart labs, what is a smart lab? Obviously we talked about it, 50% or more on savings. We want deep energy efficiency. We won't compromise safety, and we want an information layer. We want to be able to have that data stream come back, and it's not just come back to the facilities manager or the environmental health and safety professional. We want that data stream to be accessible to the PI in that laboratory, that undergraduate student who's working in that lab, who's interested not only in making sure that the lab's performing as it's supposed to be performing, but that they're able to say, well, maybe if I have an excursion, I see something that's going on with my research animals that's different, I don't understand it. Well, can I look at data that's coming out of my laboratory on airflow, on lighting, on any of these things that I can now trend and record on temperature? So being able to take that data then and incorporate the data from the actual laboratory into their research. Again, all these pilot projects, right? We've done all these as pilot projects before we incorporated them into the laboratory. And we want to basically make sure that the theories that we have actually work in practice. Are these retrofitting or new construction projects? They're actually both. We've done retrofits. We've done retrofits on 13 lab buildings to make them complete smart labs. And we've done the new construction project that was Gross Hall. It definitely can slow your project down. You have to storyboard the exact work, but you can do these retrofits that we're going to show you today in occupied lab buildings. You can sacrifice schedule for keeping that building in operation. And basically, all the different stuff you're going to see today has been done at one time or another in an occupied building. There's a huge amount of communication that has to take place. You have to communicate to the people who are working in that building. You have to communicate to the contractor what your expectations are of keeping systems in operation, and when you do need outages, how you're going to plan for those outages and let people know that those outages are coming. And Peter and Don know about another one of our techniques for planning construction in occupied buildings. I'm not going to share it with you, but if you go ask them, they'll share it with you. So where did we start? We started with a number of buildings across campus. All of these buildings represent multiple types of sciences. We have engineering, physical sciences, atmospheric chemistry that was represented, chemistry, biological sciences. So all of these different types of buildings are represented. And they all had an estimated air change rate that we thought was 6 air changes per hour. And as Wendell told you earlier today, those air changes had crept up over time. Now that can be because we've come in and we've added snorkels, we've added gas cabinets, those kinds of things. And nobody said, well, let's reduce the general exhaust. They just added more supply air. So pretty soon, your air change rates in those rooms creep up higher and higher and higher. Constant volume or variable volume, where did we start? It's important to know that we've done both types of retrofit. And then, as Wendell also indicated, more efficient than code. A lot of these buildings started much more efficient than code. Some of them started as LEED Gold. Some of them started as LEED Platinum. And we still went in and did retrofits in these buildings. So just because you've reached the US GBC point total does not necessarily mean that you have the most energy efficient lab building that you can possibly operate. So we'll get back to that slide when we get to results. But that's where we started. Why are the savings possible? I think a lot of people in the room know just how much stuff is going on in these laboratories. Wendell went through, the fact that the air is once through and what that means, and we've talked about the illumination levels. And you do have a large number of equipment that's not even lab equipment that's running 8760. So there's a huge amount of savings that are completely possible. Wide range of paybacks, right? Our price that we pay for energy in Southern California is much, much different than it is here. However, what you'll see and what we did here was we tried to take one of our Smart Labs retrofit projects and run it across an entire portfolio of possible energy prices. And then natural gas being very much tied to electricity prices, especially in Southern California, because of the fact that the last kilowatt hours are usually generated with the gas plants. This kind of gives you a range. So from 4 cents a kilowatt hour and about 50 cents a therm, you're in the 10.2-year range. And then you can scale that all the way up till you get to the more expensive, and you're down in like the 3-year payback range. And I ran these numbers actually without an incentive because a lot of places you cannot get an incentive from the utility on your retrofit project. So again, your mileage may vary. We're talking about different climates. We're talking about a whole lot of different things. But you want to know that the paybacks are possible. Again, why are the savings so big? Because the savings are not linear. Especially when you talk about fan energy, pump energy. For the non-engineers in the room, I gave you a very quick math problem, and I even solved it for you. But what you can find out is that a 10% reduction in the speed that you're running that supply fan or that exhaust fan results in a 27.1% horsepower reduction. Okay? So 100 horsepower supply fan is not abnormal in a giant, 150,000 square foot lab building. And we're talking about enormous numbers of kilowatt hours. Now that's on just your supply fan. So then if you have your supply fan, you have to have an exhaust fan. So you can repeat that savings. The numbers add up very, very quickly. Engaging the campus. I think this is one of the things that UC Irvine does very, very well. And I think this is one of the things that when we talk to people, a lot of other people struggle with, is how do you engage your stakeholders, your PIs, your people on your campus to let you come in and do these retrofits? Well, we do a really good job with town hall meetings. We plan the project, we bring it to key stakeholders, whether those are deans or assistant deans. We tell them about the project and we say, hey, we'd like to have a town hall meeting with your faculty and staff in that building. We want to explain where we're at, why we're doing it, what the climate portion of the project is, what the deferred maintenance portion of the project is, how it's going to make the building better, how it's going to affect the people who work in that building and what they can expect. We don't leave it there. We have another meeting right before construction. Just a reminder, everybody, this is what's coming, this is what we're going to do, this is the effect on you, and we want to make sure that we've communicated that not once but twice. And we know how hard it is to get people to show up, but we can then send out the PowerPoints that we use for these meetings through the email distribution system, and everybody at least gets a copy. Post-construction follow-up. If you want to build a good rapport with the people who work in these buildings so that you come back next time, or one faculty member in one building talks to another one where you're about to do your next retrofit project, you want to come back, show what changed, follow up any on post-construction issues. I don't like this about my lab now, or I have this issue in my lab. One of the ones that we struggle with is now it's too quiet in my lab because they don't have that high volume of air whooshing around. They don't know what to do without it. So those kinds of things. And then providing training. Training on all the systems you put in, whether those are dashboards, how to use them, lighting systems, et cetera. So moving on, prerequisites. Are there things that we do first or that we consider a foundation before you can move forward with a smart lab implementation? And that answer is yes. And this is the quick set. It's you've got to get to these different prerequisites. And the first thing that everybody talks about is the constant air volume to variable air volume. And I think this is kind of a standard of design. Everybody around knows that you should probably be into a VAV system. And whether you're using lab air control valves on the supply and on the exhaust or just on the exhaust, you can basically make your lab dynamic. You want to have dynamics in the laboratory. And you're going to hear that a lot today. You're going to hear dynamics in lighting, you're going to hear dynamics in the mechanical system. Talking about raising and closing the sash, that's dynamic change of how much air is flowing through that fume hood, right? So I caution you. I caution you to say, yes, we purchased a VAV system for our building. Our hood is VAV, close your sash, okay? If you have high air change rates, this can be the scenario that you have. This is us trending air change rates in a single fume hood laboratory on our campus, and we expected, it was VAV. We paid for the supply air valve, we paid for the exhaust air valves. We put all this to work, and we tell people to close their sash. Unfortunately, what happens is when you close your sash, your general exhaust valve opens. And when you raise your sash, your general exhaust valve closes and your fume hood exhaust valve opens. And so even though you were doing what was proper, you weren't actually saving any energy. You were just changing the place that the air goes. So understanding these systems a step beyond just saying, I have a VAV system and close your sash, really starts to change how much energy savings and how much actual impact you have. And you can find these kinds of examples throughout our talk, whether it's going to be on exhaust deck discharge velocity, where you're talking about closing the bypass because of your roof, or reheat. All these different things are making sure that your dynamic system is actually dynamic. So typical research laboratory prior to retrofit, you start out with your constant volume control valves on your exhaust. Everything is hard balanced. You also have constant volume dual duct mixing boxes. This happens to be a dual duct example, not single duct with reheat. But a fairly straightforward retrofit where you're going to change or upgrade those valves to variable volume. You still have your mixing boxes, which are making temperature, but now you have added a control valve to actually make flow. So on your dual deck example, whichever you choose, you have a few things to look out for. And this is all in the prerequisites, right? So static pressure must be equal. If you do not set the static pressure on the hot and cold decks equal, you will backfeed one into the other, and you will have a very difficult time making temperature. So these are kind of the lessons learned, right? There's things that are, you know, it is possible to retrofit these buildings. It's possible to do it without ripping out everything and going to terminal reheat. But you have to understand that there are challenges within the system. So we've made our temperature. This is going to make temperature. We set up the system to do that. And now we want to make flow. And so we put in our laboratory air control valve, whichever company you want. And we missed that, so we should have put, you know, lab control valve. But you can use anybody you want, and you're going to make your flow. Pneumatic control to direct digital control. Pneumatics in your building is probably the most expensive utility you have in your entire building. Compressed air is very expensive. Chances are you walk past thermostats all the time and you hear them leaking. So that's energy waste right there. Beyond that, no one ever has calibrated any of those ever, pretty much guarantee it. You also have all kinds of other things, right? You can't take advantage of computer-controlled master resets using pneumatics. You have to have it on the digital side. You really can't diagnose rooms that aren't making temperature or rooms that are always calling for cooling. You're not going to be able to do that until you're on a digital system. So that really opens a whole new set of ideas for you to be able to work in. Manifolded exhaust. We heard from Harvard this morning that they definitely get this and understand it. Unfortunately, you go campus after campus and you still see the single exhaust fan being served by the single hood being served by the single exhaust fan. You don't have an N+1 design. Right there's a safety question. What happens when that belt breaks and somebody's working in that hood? You know, especially if they're using something that could be exposed to them very, very quickly, where they're depending on that hood to provide that safe area to work in. You don't have the opportunity to be variable frequency drives on your fans, et cetera. So manifolding that exhaust, that's a project that we've done actually as a retrofit project. It's more complicated. It takes time. You have to set a temporary exhaust fan. You have to connect all these temporary exhaust ducts as you pull these hoods off or pull these fans off the roof one at a time. You have to go back, build your manifold, set new fans, and then reconnect everything. But if you do it one at a time, it's totally possible. Constant flow to variable flow. So if you are in the terminal reheat situation and you have three-way valves, going from three-way valves to two-way valves and using differential pressure control. Fairly simple concept, great opportunity to go in and do a deferred maintenance project, put in a better reheat coil, all of those kinds of things. So all considered kind of prerequisites. It's all laying the groundwork for being able to build on that with a true smart labs concept. And then fixing the known. This is the one thing that you're going to find when you go in and start to do retrofits on your laboratories, is chances are, because you're currently flying blind, you don't have a dashboard that trends all these different points with easy to read graphics, you're going to go in and find lots and lots of failed components. Even though you think the lab's working perfectly, and you can probably even go put a flow hood on a lot of stuff and measure it. You're going to find reheat coils that are leaking by, broken actuators, dirty, ducts, all of these kinds of things. This is your opportunity to go in, make those laboratories safer, and fix a lot of the things that you didn't realize were existing. So expect to spend contingency dollars as you're going through the project. But are they really contingency dollars? Well, no, not really. They're really deferred maintenance dollars, and you're just spending them now. And then location, location, location. Everybody goes in and builds the lab in their nice big open labs. And unfortunately then, PIs come in and ruin your nice new lab. And when I say ruin it, I mean what they do is they put equipment, whether it's a vacuum pump next to the thermostat or an ultra low temp freezer next to the thermostat, these kinds of things, or a kiln or anything else that we've found. They also tend to say, well, I really didn't like the snorkel that was here, so I created my own snorkel. I went down to Home Depot, got myself a shop vac hose, cut a hole in the ductwork, ran it down. These are the things that you can fix with location, because now the research lab's been occupied. So you can go in and hopefully modify what's been done to make it work more appropriately. So moving on, monitoring and verification. This is a prerequisite as far as UC Irvine is concerned in our program. When I say monitoring and verification, what we're really going to be talking about is metering and submetering. So we can talk about dashboarding later, and we'll talk about how we monitor those things. But when we talk about monitoring and verification, we want to make sure that the retrofits and the stuff that we're asking people to do and the paybacks are actually happening. We want to baseline that building and get a good idea of what the energy use intensity is. And we want to normalize that data. So when you ask yourself, where are you at, you can just ask these questions, write down the answers, and then you can see where we're at, do a comparison, find out if you think that's a good approach. You can definitely, I think pretty much most people have the total building energy use. The question is when you get down to the zone level, do you have those capabilities? If you don't have those capabilities, well, then how are you really making the determination of, yes, this building has a high EUI, but I don't know where, and I don't know why. And it could be completely driven by a single professor's laser or magnet or whatever they have. You know, it could just be a freezer farm in the building. But once you get beyond that, it's really hard then to find the other energy drivers of that building. So understanding that you can get down into the zone level and really start to meter and monitor that is what's going to be incredibly powerful. Building management systems provide decent graphics now. Paying to have those graphics built out is not cheap. But having that ability to go in and see what your duct pressures are, what's going on in the building, which boilers are running, or which heat exchangers are operating and at what level, really gives you a lot of feedback on the building. But electricity is always going to be a key component. So for electricity for UC Irvine, we've struggled with this for years. This is the piece of technology that works best for us at this point. And it is a 12 and 24 channel meter. It's made by a company called Melrock, but you can find other companies that do something similar. Simple coil CTs that snap on. You plug this in to the internet with an Ethernet cable, pops right in. It feeds its data to the Amazon cloud. It is 1 hertz resolution. So if you really need 1 second interval data, it will provide it. We have 1 minute interval data on campus, and we're going to look at some of that. Does pretty much everything you'd want to do. Because you're picking up the potential, you got power factor, amps per phase, everything that you'd want. Sensor accuracy is very, very good. People will say, well, is it revenue grade? No, it's not revenue grade. But you pay for revenue grade. You don't need revenue grade, but everybody asks if it is. So what does it look like installed? Here's an install in one of our lab buildings at UC Irvine. You can see here we have a 12-channel meter here and another 12-channel meter. I think this is a 24-channel meter. This is what the CTs look like when they're clamped on inside of a panel. Here's the main building income with other CTs clamped on. This is a very, very easy install, and it provides an enormous amount of data. And what I like to do is, the way that we've structured this is, give me the main income of the building. Definitely have to have that. Then let's go out and let's pick up the motor control center. Let's pick up the lighting if we can separate it. Let's pick up the plug load if we can separate it. But give me the motor control center and the main of the building, and then pick up whatever other loads I can get easily and quickly. It's going to allow me later on to be able to do a lot of visualization of my lab energy use. Some labs we've metered much further than others, where we can do floor-by-floor comparisons of plug load in this floor versus plug load in another floor. We actually did a Labs 21 or I2SL presentation where we've actually put in almost 1,200 CTs, and we borrowed them for the company. We metered an entire lab building down to every single plug, and then we pulled all that back out. But you're going to see some of that data. We couldn't afford to keep it, but it was nice of them to loan it to us. Drill down on your demand then. So now I know what my total building is. I can start to drill down on that, really see which floor or which section of the building is using the energy. Baseline data, 1 minute, 15-minute data every day. I can set my min, my max, all these kinds of information. The nice part is that now I can start to set up metrics. I can set up metrics to know whether or not I'm meeting the 50% reduction, to make sure that I'm getting the payback on my investment, and I can maintain that payback. So there are current metrics. You get the watts per square foot, the EUIs, the kBTU per year, those kinds of things. Those are great when you're talking about high-level, building-level energy benchmarks. Unfortunately, the real energy way to save energy is down again, at the zone level. If you have good monitoring and verification capabilities, you're going to be able to set different metrics. And those metrics are going to be powerful because you're going to be able to take action on those metrics. So with that, we've gotten through the prerequisites. Now we can get into our first kind of piece of the laboratory, which is, for us right now, lighting. Lighting seems to be where most people start. We figured that's where we should start today. And so again, what do we want lighting to be? We want it to be dynamic, flexible and dynamic. We want people to be able to take advantage of the fact that we've put in some sort of ability for them to control their lighting, that we can save energy automatically, and we want to encourage people. We want to have that conversation. Be conscious of your lighting needs. And we'll look at ways that we do that. So we started out by saying, well, what's the lighting power density of the space? Lighting power density is just watts divided by area. And then when you want to get more complicated than that, you have to multiply in the occupancy sensors or the daylighting sensors and take advantage of the savings that you can get from those things. We've worked very hard on campus to reduce the lighting power density. However, we've worked very, very well with a lot of our researchers on campus saying, where do you need the light? How do you use the light that's currently in your space? And can we help you and can we improve on that so that we can save energy? The very first thing that we've done, and we've done this across campus, not just in our research spaces, but we went from the 32-watt T8s to the 25-watt T8s, and we went from a normal light output ballast to a reduced light output ballast. So we're underdriving that 25-watt lamp. This has been an incredibly effective linear fluorescent solution across campus. It's worked out very, very well. If you have a lot of buildings that are very, very cold, you will struggle with this. Don't put them in cold rooms, and if you have to run certain laboratories down in the 60-degree range, you're going to struggle. The 25-watt lamps, when they're underdriven, there's a lesson learned, don't work that great. However, anything else, it's a fantastic solution for. Automatic daylighting controls. Automatic daylighting controls have taken leaps forward in just the last 5 years. When we built Gross Hall, one of the key aspects of Gross Hall was everything within 15 feet of the window line, private offices, conference rooms, laboratories, would have automatic daylighting controls. What's gotten better about these is the calibration, the auto-calibration and the recalibration of these systems. When we built Gross Hall, we put these in 15 feet of the window line. You build out a nice laboratory with white floors, black countertops, nice white reflective shelves. They calibrate the system, and then people move in. When they move in, they bring in all of their different equipment, right? They cover that lab bench in that little section of foil. I don't really know why they do that, but they always do. They also bring in, of course, all of their equipment, their books, their beakers, everything else. They occupy those shelves, and they change the reflectivity of the space. Well, when you change the reflectivity of the space, you change how the photocell up there is calibrated to seeing how much light. So all of a sudden, the lights start to do things the researchers don't appreciate. Again, this is about going back, interfacing with those people. This is the lesson we learned. And once you've done that, you know, okay, next time I do a daylighting project, I write in 6 months from now, contractor has to come back and recalibrate the system because it's going to take 6 months to occupy this space. It's going to take a year, write it right in the contract. That's your opportunity. Other daylighting opportunities, and daylighting opportunities, of course, without glare, because yes, you want to get the daylight into the space, but if you're trying to work on a computer monitor or you're trying to read something, the glare is going to make it impossible. There's a couple of choices. You can go with the light shelves, and then once you have the light shelf, these look like mini blinds, right? Upside down mini blinds. They're actually polished mirrors, and they do not move. They are built into the glass, or they can be just outside of the glass. But they take that light, they bend it and reflect it right up onto the ceiling. They make really nice rectangles that move across the room during the day and provide some really nice diffuse light into the space. Perforated window blinds. What a simple solution, right? When you actually are speccing out a building or you're going to go in and do a retrofit, don't go back with a solid blind. Go in with a perforated window blind. Unless it's a specific laboratory that has a specific reason to have complete darkness, which you can accommodate, the perforated window blind makes sure that even when people decide, I don't want that direct light in my space, you're still going to get some of that diffuse light. And then a good sequence, a sequence of operations that allows people to make use of the amount of light that they need, and you can provide additional when the task requires it. So auto on to 50%, manual on to 100%, and auto off. Simple concept. Most of the time, though, I think when you see this, you see auto on to 100%, auto off, right? We also took that one step further. We know in our big open lab bays on campus, and this is just one big long open lab bay, and then you got your support research space, and then another big long open lab bay. These are about 3,000 square feet that you'd probably have to have 3 or 4 occupancy sensors going along here to be able to pick everyone up no matter where they're at in the laboratory for lighting, right? But that's not how the space is assigned. So what used to happen was you'd have the lights along the windows. That'd be on one circuit. Down the center would be on another. And then down the support columns, a lot of times where the equipment's lined up might be on another circuit. If you assign the space like the color codes indicate, shouldn't you put in the occupancy sensors and circuit the lights the way the color codes indicate? So what we have now is we have the lighting in this area on one circuit, this area, and they each have their own occupancy sensors, so that when this person decides to work from 6 in the morning to 3 o'clock in the afternoon and do their research, and then this person here, they're a night owl, and they come in at 4 o'clock in the afternoon, work till 3 in the morning, I don't have to waste that energy having all of the lights on just for one research bay to be occupied. And then magnetically mounted task lighting. So if we've lowered our lighting power density, and we want users to be conscious of how much energy they're using for their lighting needs, and that they still have to do fine pipetting or whatever it is on the benchtop where they're going to be doing work, we provide them with magnetically mounted task lighting. Put it where you need it, but don't put it everywhere, right? Because if I have a large piece of equipment, whether that's a shake table or something to that effect, well, I don't need that magnetically mounted task lighting there. So we give them this, we give them the option to put it where they need it. Unfortunately, what we didn't do was explain how to install it. This one's installed backwards. You're not supposed to look at the LEDs. But it makes for a really good picture. So don't forget about your stairwells and corridors. If they're on 24/7, they don't have to be, and they definitely don't have to be on at 100%. So we've done bi-level stairwells, we've done bi-level corridors across campus. We believe that the smart corridor is an excellent lighting solution to save you a lot of energy across campus. We've now started to actually go back and retrofit our bi-level stairwells already, replacing the fluorescent tube with LED tubes. So we're constantly upgrading and taking the next step. And then, of course, you have synergistic effects. Right now, you probably like the fact that your lights are pumping out lots and lots of heat because your spaces are cold. For us and our climate, we're constantly fighting the cooling issue and not so much the heating issue. So for us, there's a huge synergistic effect of lighting by reducing that lighting power density and getting those watts out of the space. Again, mileage may vary, but here's the formula that you can take away and figure that out. And so it takes that fraction of the year of cooling into account, and you can get those synergistic effects. Now, again, remember, you're only going to see that savings. It kind of goes back to the fact if you have the high air changes, right? If you're pumping that air out at a high air change rate, there might not be a synergistic effect. Synergistic effect only takes place if your lighting is actually driving your cooling load in the space. So mechanical system. Again, just like lighting, want it to be dynamic. Give the people the ability to have a dynamic system that responds based on what they're doing in their space, whether they're there, whether they're not there, whether they're doing something intensive where they have the fume hood in use or they're not. Maintain that level of safety. It's key. Has to happen. If not, what we really want to do is we want to talk about augmenting the level of safety in these laboratories. Right size the equipment. Systems are so oversized most of the time. So if they're oversized, chances are you're losing out on that savings that's there. So let's take a look at it kind of from a really simplistic atmosphere. Mechanical system balance, right? So right now, you have all of this equipment in your laboratory space, and you have maybe these kinds of air changes. And if you're supplying 55 to 60 degrees supply air temperature, you have to add reheat to bring it into balance. And then you can balance out at your high air changes, not a problem. If we take that reheat away, system falls out of balance, right? You want to drop those air change rates, and you still have that reheat. What we really want is we want that balance. So where is that balance at? Where is the balance of all this equipment in the lab, plus my skin load, plus my lighting load, and where does that balance out with a supply air temperature in the 55, 60 degree range? 2 to 4 air changes per hour. How do I know that? Kind of goes back to the fact that I told you we brought in that company and we partnered with them and we said, how many sensors can we get? We really want to monitor these spaces. And we started looking at plug load in these laboratories. And there's a lot of plug load in these laboratory spaces. And we were able to go in and meter all this. We were also able to go in and meter support spaces with your biological safety cabinets, those kinds of things, and your freezer farm spaces or your equipment corridors. And what we found out, sorry, hard to read, I'll explain it for you, is those equipment corridors that are at the very end, they actually do almost reach your 10 watts per square foot. Interior spaces, let's say this is, and that's 9% of your space. 9% of your space was that high density equipment. Interior spaces, 26% was that support space where the biological safety cabinets were shown. A lot of times they also have microscopy rooms in there, those kinds of things. 65% of the space is open lab bay, those big open labs where I drew all those red arrows showing you how many things were plugged in. Where are those running at? Less than a watt per square foot. Less than a watt per square foot. Why? Because it's all plugged in, but you're not using it. Most of that equipment you use one piece at a time. So, designing and ventilating for 10 watts per square foot for 9% of your space when 65% of your space is running at 1 watt per square foot makes no sense. So think about your mechanical system now. Was it oversized? Yeah, probably. You know, are you pumping way more air than is required to try to satisfy this space? Yeah, and how are you making up for that? How is that room not 55 to 60 degrees? Well, you're adding reheat. So there are certain spaces, and we showed those, that 5 to 9% of the space where you do have heating issues, and you have to be able to deal with that. One of our solutions has been putting in dedicated exhaust and allowing those spaces to run a little bit higher temperature. So basically we've taken and said, okay, in our freezer farms or in our equipment corridors, we want dedicated exhaust grills. And those exhaust grills happen to be a lot of times right where the equipment rejects the heat, so we don't let that migrate into other spaces and then drive our air change rates up. You also see that the wall here for the equipment corridors traps that heat. So we basically make sure that we try to hold that right up near the ceiling and deal with it before it can migrate into other spaces and cause those spaces to have to absorb that cooling load. We saw earlier where I had it laid out with green blocks, and then we looked at the lighting. These are your big open lab bays, and we have these equipment corridors. They're shared equipment corridors that we ask all of the ultra-low temp freezers, and we ask all the incubators and those kinds of things to be stored in so that we don't transmit that heat gain out to those open lab bays, and they're shared corridors. They're designed this way. They're fire marshal and exiting approved. They have magnetic hold opens on the doors so that you don't have people who are gloved up having to open doors to get to these corridors. These are well thought out and well designed spaces. So with that, bring up colleague Mark Gomez.